So diffusion models, when I think about what diffusion models actually are, they consist of an image and they try to add noise iteratively on this image and try to predict what the noise will be added. And they try to denoise it to get to the original image. So it's a combination of predicting what noise will be added to an image and then removing that noise, predicting, identifying what is actually noise to get to the actual image itself, and then they can generate new images based upon that noise and identifying what is noise versus what is not noise. So that's diffusion models. Autoencoders are representation models where they try to learn a latent representation through the encoder. So what the encoder is going to do is it's going to try to learn a hidden representation of, say, an image. It's going to take an image, say 28 by 28 matrix, and it's going to learn, let's say, depending on what the encoding dimension is, it's going to learn a hidden latent representation. Let's say it's 664. And now a decoder, and again, this latent representation is not directly interpretable by humans. It's abstract features that the encoder learns from the original input matrix. And the decoder takes that encoding, takes that output from the encoder, and then tries to reconstruct the original image. And the deviation from the reconstruction from and the original image from the original image is the reconstruction loss. And based upon that loss, we then back propagate and update the weights of both the encoder and the decoder. So a typical training loop has in each epoch is one pass of the training set. And we typically do this in batches. So let's say a batch size is 24. What it's going to do is epoch, for each epoch, and then for each batch, it's going to reconstruct the original image, compute the reconstruction loss, and then at the end of each batch, we're going to update the weights at once. Update the weights of both the encoder and decoder after we have identified the reconstruction loss and the gradients, and we're going to back propagate and update the weights. So that happens for each batch. Right? And for each epoch, we go through all of the batches in the training set. So each epoch covers one training set, one pass over the training data set. And discriminative models are your typical classification and prediction models. So your regression, your classification, your XGBoost gradient, your linear regression, logistic regression. Generative models try to learn the underlying distribution of what the input image is and then try to generate new images or new text or new data points from that distribution that it learns that the input data is based on. And so that's at a high level of what autoencoders, diffusion models are. Now we'll go into sort of a new idea on optimizing efficiency in NFL play calling. So we have three different paradigms or models we want to look at. First is a play prediction model to model what the coach will actually expect to call in a given situation. So given the state variable, the game state variable, what is the probability of a run? What is the probability of a pass? That the coach in that situation will call. So probability of a run, let's say 70%, probability of pass 30%. So this is trying to model the coaching behavior. Trying to model what is the coach expected to do? What is the coach expected to do based upon the game situation? And we can also include the prior plays as well. Could also include, so it could also be a temporal sequence, right? We could also include the prior plays, can include the weather, can include the opponent, can include the opponent defensive look on that play. So what is the coach going to call given that situation in that time in the game? What is the coach going to call? Expected. What is he expected to call? Not even what he actually calls, but what is he expected to call? And that is the reason why we want to try to derive an expectation is because an expectation gives us a range of probabilities. Probability of run is this, probability of pass is this. Observed is just a binary, he passed or he ran the ball. So it could be a coach could actually be 50-50 and if he wants to run, but the observed would only just be a binary, like he just ran the ball. We want to try to classify the uncertainty in, or we want to quantify the uncertainty in the coach's decision in deciding whether he wants to run or pass the ball. And so to quantify the uncertainty, that's why we have probability of run pass. That's why we were trying to predict what the coach will expect to call. So this is coach expect to call, right? Expected play call, expected probabilities of play calls, expected probabilities of play calls. Now, what should be the optimal call, right? What should be the optimal call? This is the second model. Now, this is from expected points added per play. So given a run, what is the expected points added? Given a pass, what is the expected points added? So what this is going to be is it's going to be game state action mapped to EPA. So it's going to be game state run, it's going to be a certain EPA. Game state pass, it's going to be a certain EPA. Now, the difference, so let's say a run gives a 0.7 EPA, a pass gives 0.2. So in this case, a run is better. Now, how much better, right? How much better? And it doesn't need to be just a pure difference, but we can quantify a metric, we can create a metric, right? We can quantify how much better, right? So how much better was the optimal play? So how much was the value added from selecting the optimal play, right? Value added. So we were quantifying the value added from selecting the optimal play, rather than the suboptimal play. So what's the value added from choosing the optimal play? So we have two things. We have expected probability of what the coach is likely to do, and we have the value added from choosing the optimal play. Now, if the optimal play has a significantly larger value than the suboptimal play, and the coach actually goes with the suboptimal play, then that is very inefficient. And so that should be expressed in our inefficiency metric, which will be, again, not maybe a difference. It could be a difference, but it's going to compare the probabilities of the expected play call and versus the value added from the optimal play to try to get an inefficiency or efficiency metric on how efficient was this play. Given this game situation, the coach was expected to call this play, and these were his probabilities of calling the play in this game situation. This is what he should have called. This is what he should have called, and this is the value added from the best play that he could have called. And then we compare those two and create a metric of efficiency for every single play. And what this allows us to do is it allows us to quantify how efficient, how good the play call was given that situation in the game, So we create a metric for evaluating play calls. Then we can aggregate this across game situation. So third down, red zone, first quarter, second quarter, third quarter, across across different seasons, across coaches, across teams. We can aggregate this, and then we can create visualizations and heat maps on when our coach is efficient, what coaches are the most efficient in certain situations, what teams are the most efficient in specific seasons. Do we see a trend in play calling efficiency change over time? We can identify those insights and create those visualizations. Now, how do we measure the success of this metric? Well, think about this metric. This metric is measuring efficiency of the play call. So it's trying to determine, quantify how good the play call is, the performance, not necessarily the performance, but how efficient, given the situation, how good was the play call. And so because we're trying to measure efficiency of the play call, what variables do we have that are actually observed? We observed efficiency of the play call. Right? This is our metric, efficiency of play call. Efficiency of play call. What do we observe? We observe the result of the play. We observe the result of the play. So in theory, if the efficiency of the play call is high, then the result of the play would also be high. Right? Now, if it was a low efficient play, then the result of the play would be low compared to what it could have been. Compared to what it could have been. So what we can do to quantify the success of this metric is try to see if there's a correlation between the efficiency of the play call and the offensive stats of the team. And so whether it's expected points, is there a correlation between DVOA, number of yards, number of expected points per play or per drive, and compare the offensive stats with the efficiency of the play calls across teams and see if there is a correlation between these two, the efficiency of the play call and the offensive. Now, if there is, then that would give some credibility to our metric that a higher efficient play call will result in higher offensive performance, right? Relative to what it could have been, right? Relative to what it could have been. So that's how we can measure efficiency of play call. We can also measure it subjectively by just saying, in this situation, coach should have called this play. Like if it's a 3rd and long, should be a pass. It should be a pass. And if the coach calls, let's say, a run, that objectively would be a very low efficient play. So that efficiency of the play call should be pretty low. So subjectively, qualitatively, we can make that assessment. We could also check the statistical significance of this metric, because one of our hypotheses is that coaches are inefficient, right? If coaches were efficient, if every coach made the optimal decision, then we wouldn't be making this metric in the first place. The reason we're making this metric in the first place is because we know that coaches are suboptimal. They don't make the correct decisions every single time. And more often than not, they are likely to make a suboptimal or sub-efficient decision. And so we want to quantify that. And so we want to see, is the expected points added of the optimal decision significantly different than the expected points added of the actual play call, the actual decision. So this difference, is it significantly greater than 0? Right? Is it significantly greater than 0? If it is, then we know that if it is in certain situations, it may not be the case for all, depending on if we do run or pass or different types of plays. Maybe in certain situations, it's significantly different than 0. But if we can prove that it is significantly different than 0, that there is a difference between statistically significant difference between the optimal play and the actual play across coaches, across seasons, even in certain situations, that there is some trend and pattern that is emerging here that proves the optimality of these coaching decisions and these coaching play calls, then that means that our metric metric achieved its goal of quantifying the inefficiency of coaching plays and play calls. So statistical significance of the metric, correlation with offensive performance, subjective qualitative assessment, also variation among coaches, situation, and teams. We should see some variation between game situation, third down, fourth down, among in the time of the game, first quarter, second quarter. Coaches are probably, you know, probably have a certain tendency to call plays in the fourth versus first quarter. So if we see that structural variation, also variation among teams because they have different players, and so they may be inclined to call different plays. If we see that variation among teams, situations, and across seasons and different game scenarios, then we know that this metric is achieving its goal. So it's really four things: statistical significance, significance of the metric, correlation with offensive stats, qualitative assessment with game scenarios, and variation among game situation, game scenarios across teams, across times in the game. That's how we can evaluate the success of this metric. And in terms of the modeling, again, play prediction model, we can do any model out there. We can test out neural nets, transformers, linear regression. It would be a classification problem if we choose, right? If we choose to go like run pass, even maybe subcategories in the pass, what type of pass, what type of run. So it would be a classification problem, so we can go with any classifier and use those probabilities. For the optimal play call, it's going to be a regression problem because we're predicting EPA, eh, predicting EPAs, and then the difference between model one and model two will be our inefficiency or metric that we can create or name for. Now we'll go through a few more GS summaries that we left off. And so we know that travels in Soda to Shrikant Swami came from Vardalasi Swami Shri's spiritual influence. Them and 800,000 devotees reached Vantali Kalyan by his invitation. And Laduma's sons arrived with their mother's invitation. Then Grace's Megpur, Goran Swami reveals that Swami's actual Keshav Jivandas cheerfully tells Goran Swami that the Ahmedabad sadhus claimed that he wouldn't attain Akshardham. And so Goran Swami then took him to Vartal. Swami then came for Chaitanya Punam and explained the importance of GS. Six purposes of SM incarnation on Earth. Swami explains, or GS explains the 6 reasons that Maharaj came onto the earth. You will not have to chop wood, so Baldin is blessed. He was going through intense difficulties and struggles. And so he asked the woodcutter Baldin's mother for firewood, and she insisted that he take all of his firewood plus 2 pieces. And then he says, because of this humble service, GS says that he will no longer have to chop wood. And then he eventually rose to become the Nawab minister of this state. Transformation of Mujasuru. Yeah, he was originally spiritual, but then he became indulgent in all of these impure activities. He essentially explained the consequences of these impure activities. And so his immediate gaze sent him into Samadhi. He saw sinners being tormented into hell, and then he finally fell at his feet and accepted Vardhaman. Then we have transformation of Varu's transformation. We have GS illness, GS finally returning to Akshardham. We have Jagabhat incidents, facing problems from home. 4 ways of enjoying what is bliss tells Jagabhat that the 4 ways are darshan, talks, prasad, and embrace. And he has the ability to grant all 4 through himself, through his association. Now let's just quickly go over PP3 mental models for these. So L12, 6 levels of faith, Sarika Nirvikop, Sarvikop was always about the comparison to humans. Nirvikop was countless millions of Brahmans, mere atoms of structure. The lowest develop highest, reverence, condemnation. Eventually fall from substance and believe oneself to be body, aversion for punch cliches. Developing aversion for punch cliches, result of understanding this glory, eminent spiritual people. Bhakti with glory is enough. Then we have examples of these four types. Not perceived Maya, similar service. Transcendent Maya, who can be considered to have transcendent Maya from conviction. Lowest can become highest. Destruction of Jeev. Afraid of harming these four. Paradox and resolution. 3-2. Attainment of all Purusharths when you realize the manifest form of God, the same way conviction for non-manifest devs. And attain company of the sun, the highest state of enlightenment. Iron nail from the fixed mind, firmly affixed to the feet of God, eternally happy. Vairagya, gateway, form of liberation, analogy, king guards, perform bodily activities, understanding like the Sitachi. Dira means train the on and mind. Magical technique 312. About fidelity, not impressed, slightly impressed on seeing other men, faithful bhakti, only fidelity towards God, not towards anyone else. Golden thread, wax thread, golden thread, same across different seasons, personal nature is the same. Sun suppresses mind, indriyas, two dangerous flaws. Muddish does not like these attributes. Vishnu here about medicine. Imagine this again, source of strength, nature of the Atma, and then the arrows are like the Vishays. And the arrows then fell and were removed from the body in the same way that you can actually remove the attachment to the Vishays. And that will stop there.